Right, it looks like our participant numbers are stabilizing, so we can go ahead and begin the seminar. Welcome to those of you this week. Welcome to this week's LPI seminar. We're very happy to be joined by Dr. Moto Ito this week, who is a senior research scientist at the Kochi Institute for Core Sample Research at the Japan Agency for Marine, Earth Science, and Technology, although many of us may remember Dr. Ito from his time here at LPI and JSC a few years ago. Dr. Ito is an expert in elemental and isotopic analysis of primitive materials found in extraterrestrial samples, including meteorites and return samples using SIMS and NanoSIMS analyses. Today he's going to be presenting the seminar Hayabusa2 Return Samples, Unique and Pristine Record of Solar System Materials from Asteroid Ryugu. We will have a time for questions and answers afterwards. If you do have questions during the talk, you can write those in the chat box, and I will read those to be answered at the end of the talk, and you'll also have the option to virtually raise your hand and ask questions at the end of the talk as well. So without further ado, I will turn things over to you, Moto. Thank you for being here.
Okay, thank you very much for inviting me for this great seminar. So I'm back. I was in the API and Johnson 10 years ago, and then almost 10 years, I worked for the marine biology and also materials from us terrestrial samples. But the past several years, I was working on the Hayabusa2 missions in deep, working with jet circulation. So today I am going to talk about our team research effort to the Hayabusa2 sample analysis. Is that okay with you?
Looks great.
Okay, good. Hi. Okay, title is a Hayabusa2 return sample, so which which is a unique and pristine record of the solar system materials from Asteroid Ryugu. This research cannot done by myself. I have a lot of collaborators here, so thank you very much for everybody. どうやったら行くんだこれ。あ、行った。Okay. People may know or do not know about my team. So my team is my team called the Field Circulation Kochi. It is here in parallel with the 6th initial analysis team led by Shogo Tachibana, and the 6th other team, of course, Yurimoto, Tomoki Nakamura, Takaki Noguchi, Naraoka, Yabuda, and Okazaki. So basically, we are independent research group with the 6th initial analysis team for the Hayabusa2 sample analysis. But here's the phase circulation team. We act as under very strong scientific direction and the ethic of the jet circulation. We can do whatever we want, but always a direction of the by the jet circulation. But this category, in Japan, we have two teams. One is Misasa, led by Eizo Nakamura. The another one is led by myself. Okay, so okay, basically, as I say, so we work with and work for the jet circulation and do in-depth legal sciences. So first important thing is we have to develop devices and tools and feedback to the jet circulation, and will be a benchmark to the international AO that started recently, and the current and the future circulation works. So our several years effort to make these devices tools, we have several papers already came out. So when you have time, please read these papers. And in parallel with this developed devices, we developed analytical technique. So especially with the integration of the bulk and microanalysis techniques. So starting from non-destructive analysis with a 3D CAT scan and Xrd to destructive analysis with the FIB and the STIXM, TM, and then nanosems. These are basically microanalysis, but for the bulk analysis in combination with SEM EDS, microprobe, and Xrd, and high precision oxygen isotopes at Open University and large geometry sims at UCLA. With these two important tasks, we did the in-depth Ryugu sample analysis. This provides a key to understand the origin and the nature of the solar system, as well as asteroid meteorite collections, connections, water rock interactions, and the evolution of organics on a small body. Okay, first thought before we go to Ryugu sample, which is about a year ago. This is a very old story. The capsule may contain small fragment. At the time, we expect to have a sample like 100 milligrams and up to millimeter size grains from surface and subsurface lesions on the C-type Ryugu. But in reality, we got 5.4 or 5.4 gram sample, which is a lot. Those fragments may be a highly porous mixture of anhydrous and hydrous minerals and organic materials based on the result of onboard remote sensing instrumentations. Okay, the second one, the highly porous mixture of anhydrous and hydrous minerals. So once we got a sample, we would like to do a best analytical result from these precious samples. So return sample, this sample goes to nationwide or sometimes international facilities. And of course, people have a lot of different instrumentations to obtain the fundamental information of each particles. The problem is the transfer processes. So because that transportation process causes severe problems in terms of contamination of terrestrial materials, sample damages, fragmentations, broken, sometimes are lost. The lessons learned from the past. So our priority was sample safety during sample transportation or handling processes. Here is the situation they have submission. So first time we did SEM investigation. Oh, this is a sample, but after CAT scan, the sample was broken, which is not good. We lost a very precious sample during the information. And also here, this is my laboratory. So we have TM and nanosems. This is made by gel, and this is Gameka. Totally different sample holder, and the different techniques need to prepare the sample. And also, even a JAX and the JASLI, which is a large, one of the largest synchrotron facility, spin rate, the distance is about 800 kilos. So these two are key to develop. For the we need to have a universal sample holder for multi-instrumentations, and also a special sample container only for the Ryugu samples. But here the requirement for the holders are easy handling in a glow box and adaptable for several analytical instrumentations, like we're focusing on nanosems and TM and also STIXM. These holders or containers should be cleaned by ultra pure water or organic solvent. Should be composed of materials permitted in check circulation. And the most important stuff is the low cost. Otherwise, nobody can buy or use that holders and facility or containers. This is a facility to facility transfer container. We use the FFTC. So many of the JSC people already have this container. The size is about that size. So first, this guy in the JAXA, then go to Spring 8. Sorry. UB-Solve, which is a synchrotron facility for the STIXM, and the sample came to Jamstack Koji, which is here, and then sample goes to NIPO. Here is ability of the FFTC. This is very good. At least several months keep the nitrogen atmospheric condition in the FFTC, so which I guarantee to avoid any terrestrial contaminations. And here is our research platform with non-air exposing system for extraterrestrial material. So JAXA helps to chamber the Spring 8. We key, how do I say? Spring 8 and Jamstack Coach here, and the UB-Solve, we all have a glove box. And then the sample will transfer with the FFTC. So all instrumentations, for example, Spring 8 is a CAT scan and 3D Xrd, has a in-house non-air exposing system only for the system. And nanosims, this is very commercial, but I developed by myself. And also STIXM, this is in-house loading system without any air exposure during the sample transportation and also measurement. This is just a quick look at the CAT scan. So this is a sample holder look like. So So this is not a legal sample. This is a small fragment of Antarctic meteorite. So here the sample mounting system is a carbon nanotube we use. When we took this image, the sample is look like this. So the sample is floating, nothing like needles or anything like that. We only obtain the sample information during the CAT scan measurement at the Spring 8. And this is a universal sample holder between starting from FIB and TM and STIXM and nanosims. So we are thinking FIB is a central port for the sample preparation of the legal sample. We prepare two different types of sample mounting system. One is only for the gel type TM. The other one is like this. So we use a commercial FIB or TM grid settled on this grid. So this can be applied to the FEI or Hitachi TM series. And after that, these two Kochi grid or Kochi clamp goes to STIXM like that, or nanosims. We prepare the special sample mounting system for the commercial nanosim sample holder. So this works. And then this is my development for the nanosims. This I spent about a few years to develop in-house sample holder with a non-air exposing system. So these process is under the in glove box. This is a real or legal sample look like. So this. So we don't have any air exposure start from the glove box into the nanosims. So which means we got very original chemical and isotopic information from the Ryugu material itself. Okay, there are a few things we know about the Ryugu by spectroscopic studies. So data from the Mu3 on board Hayabusa2 indicate that the Ryugu might be composed of the similar to thermally and or shock metamorphosed carbonaceous chondrite like Kitazato, or a closest match being the CY proposed by King. And also low albedo of Ryugu can be explained by the presence of abundant carbon-rich component in combination with the grain size, velocity, and the space weathering effect proposed by Matsuoka and Pilogret recent publication on the Nature Astronomy. Okay, this is open questions by spectroscopic observations by Ryugu. So what we observed is Ryugu is a spectroscopy very homogeneous with hydration features and also OH features caused by solar wind implantation different from the moon. The CM is the best match or CY. And the questions here is how about the micrometer scale structures, textures, and elemental abundances? So for the log ratio and the gas rotation on the parent body is the second one. The third one is if we have we can do, so we may see some depth profiles to find the solar wind implantation to compare with the moon. And finally, a hint for the age of level pi original parent body formation. These questions may solve by integrated analysis of return sample. Okay, here's the large-scale sciences. What we are currently thinking of is the smallest one is micrometer to millimeter is samples from Ryugu. So we can do, here is a coordinated microanalysis. And this, if we have this size, the bulk analysis of the sample by these instrumentations. And we have a lot of knowledge based on the based on the meteorite and micrometeor studies, like millimeter to centimeter size. And also the spectroscopic data by remote sensing on board is measured to this size. So of course, there is some gaps or some overlaps between each information, but this time, so we are trying to connect different scale chemical physical information of the different scale instrumentations. That gives us a better understanding of C-type asteroid. Okay, we are pretty much ready for the Ryugu sample analysis. So we are proposing integrated bulk and microanalysis here. So microanalysis is based on the our expertise is TM and nanosims and the 6M ZENS. And the sample is of course prepared by FIB to acquire complex microtexture and the chemical characteristics of the sample in sub-micrometer scale. For the bulk analysis of the sample, we use a combination of laser ablation, ICP-MS, Raman, and semi-EDS, microprobe, Xrd, and a large geometry SIMS, and the neutron activation analysis. This provides a measure and trace elemental compositions, DNG bands, mineral identifications, and the crystallographic characterization isotopes in bulk. Okay, microanalysis here. So basically, we start with a synchrotron CAT scan, and then did show a little bit by the field emission SEM to acquire phase identification, texture observation. And then prepare a sample by FIB. The sample goes to STIXM ZENS to to obtain the specification of element, especially that we are focusing on the carbon type of bonding and the chemical species. And after that, the sample goes to nanosims to do isotopic imaging of the hydrogen, carbon, and nitrogen, sometimes oxygen. It's depending on the time. This is very time-consuming analysis. Finally, the sample goes to TEM. So to do researches of mineralogy and crystallography in fine-grained materials and organic assemblies. This is about chemical analysis. So of course, we would like to have some time scales, formation processes, and some history of the Ryugu sample that corresponds to direct constraint on the physical and the chemical conditions and the C-type asteroid planetesimals at the early solar system. The solar system elemental abundances, so we may compare with CI. The important stuff is the gas activity on the Ryugu asteroid. Okay, the three major questions of my team. What is the Ryugu sample? Compared with current knowledge of meteorite return samples, the Itokawa or Stardust comet sample, and IDPs. Made of what? The hydrous and the anhydrous minerals and organics, soluble or insoluble. This time, my team doesn't have any ability to detect the soluble organics, only for the insoluble organics at this moment. And also a three-dimensional internal structure we would like to have, because we use a synchrotron radiation, high resolution CAT scan images of each particles. And when, where, and how did the Ryugu form? This can be solved by the mineralogical, textual, chemical compositions, crystallography, stable, and radiogenic isotopes, and measure and trace element. This is our questions. Okay, based on the questions, we expand our Ryugu sciences here. So basically, we repeat the same thing, the first one. The second one is the origin of the solar system starting materials. So perhaps this can be answered by abundances plus a Lagrange or different what kind of process grain in there. And thirdly is a space weathering erosion process on the C-type asteroid. And the fourth is gas activity on the C-type asteroid. And nature and especially distribution of both, especially we are focusing organic component. And the relationship to the associated minerals like phyllosilicate and carbonate. But this time we are focusing on phyllosilicate. You may know the sample look like. This was happened almost a year ago. So first time I saw this, how do I say, the container opened live streaming. So I was so happy. Oh, this is our samples to spend a year. This is just right after the sample opening. We went to the JAX circulation, and then these are very organized. Some of them went to the JAX circulation, so you already saw, or if maybe Johnson has several samples already. So this is Akira Yamaguchi. These are our team members. So by the way, this is me. And here, this is, we started analyzing Ryugu sample last week, a year ago, June 19th, June 2023, starting at a sting rate. So all sample preparation you can see is a glow box. This is Toriyada and Masanao Abe. This is a sample case. We did not use any airplane. We use a Shinkansen, which is a direct train from the Yokohama to the station, Ayo station near the spring gate. It took about 4 hours, but it was fun. And here is the first sample look like. So this is a FFTC. So this sample is the largest sample we got for the phase circulation Kochi. Is about 4 millimeter and 3.5 millimeters. The first time I saw this sample, oh, this is huge. It's totally different from Itokawa or Stardust acometer samples. Yes, so as I say, so all sample preparation in a glow box all the time. So this is memorial scene at the spring gates. So Akira Yamaguchi, Naoya Imae, and Nakato and Yogata, Jack's creation, this is myself. All people in my team did this type of sample handling during the spring gate campaign because this is this analytical campaign for a year. So everybody has to do their own sample preparation. So I think that we need to this type of training first time. So sample was, of course, some of the sample are embedded in epoxy, but some of the sample should divided by the tipping processes in a glow box. So you can see the tipping process like this, look like. The sample was divided by 3 or 4 pieces in a glow box. You can see this. So we pick up each grains by data, and then each sample goes to the different containers. And they start, some of the sample goes to Open University for the oxygen isotopic measurement. Some of the sample goes to FIB, blah, blah, blah. Here is the first, this is a team. So, you know, this is a famous Tsuchiyama, and this is my team. So this is look like, this is the first shot of the sample. I think this is A0002 sample. Okay, there, this is 8 samples. First, we supposed to have 100 milligram for 2 years analytical campaign of the phase circulation. First 6 months, we only have 50 milligrams because the tremendous effort by JAK circulation is focusing on the initial analysis team. We only have half. But this is enough for the 6 or 7 months analytical campaign for small party. But here 8 samples. So after we took high resolution CAT scan or Xrd or Xrd, we did everything. So this is the largest sample, and then some of the sample goes to microanalysis. Sample microanalysis. Some of them are bulk analysis. A bulk analysis means the fragment was embedded into the epoxy in the glow box. And then some fragment goes to Open University for the oxygen isotopes. Some of the sample goes to SIMS at UCLA, and some of the grains goes to INAA in Japan, and also some of them goes to Xrd to acquire crystallographic information. But again, so bulk analysis, high precision, and the same as INA, Xrd, those samples exposed by X-ray, very strong X-ray irradiation. But here for the microanalysis, we are focusing on the organic component. So these samples is, you can see some leftovers here, like black dot here. So we use these fragment to do a microanalysis. These fragment came from this main body. Okay, this is a simple flow chart. The 8 samples. This is the first time we did a quick high-resolution CAT scan, and some of them are XRD, or many samples go through XRD and INAA and laser formation, and some of them goes to this microanalysis scheme, or some of them goes to bulk analysis main like this. So we it took about 7 months to finish these 8 sample analysis. Okay, this is fun time. This is C68 Ryugu section, Ryugu epoxy mount section looks like. So this is a reflected image. Of course, we did a polishing, but no fluid use. Then lead lesion, this is a magnesium, calcium, ion, and sulfur images. Lead lesion is mainly composed of the ferrosilicate, green is carbonate. The carbonate is dolomite, mainly dolomite, and some blunite, and the base layer of the calcite. And the blue lesion is magnetite, and the yellow is a sulfite. So this is if you take a closer look, the white square, so look like this. So basically, all of the sample look like this. So of course, it's depending on some variations. For example, here you can see a modal abundance of some difference in the samples. So lowest number of the ferrosilicate is 837. This is a lot of carbonate in here. So the others are about 75 to 90% of the ferrosilicate. But interestingly, we did not observe any ferrihydride. And here is some memo after CAT scan analysis. So this is if we compared with other CI materials with the previous literatures by King and Affling. So this is very consistent with modal abundance is consistent with CI abundances. This is a 3 ternary system SI MZ FE microprobe dataset, and this is the STEM EDS dataset. So this our sample A37 and C68 is very comparable with the CI dataset. And here is a bulk Xrd analysis result. So blue is a Ryugu C787. This is a mixture of A29, A37. Because of a very limited amount of the sample, so we decided to use a mixture of A29, A37 sample. But here two sample is basically identical. We did not see any difference in terms of mineralogy or mineralogy. And if we compare with OGAI and CY and CM, so this is different from CY and CYM, but looks like very similar to OGAI, but some difference because OGAI shows antigonite and gypsum in here. So we are thinking these two gypsum like ferrihydride materials is a terrestrial weathering process. And if you take a closer look like TM level, so this is the, you can see pyrrhotite and pentlandite and serpentine like this. And the serpentine ferrosilicate looks here is some intergrowth with the saponite and serpentine. So this characteristic is very popular in the legal sample. And here, the left-hand side image is the high precision bulk oxygen isotope analysis. So this is a 98 result. This is the lowest number of the Ryugu. And here, the blue This blue is C68. And of course, we provided Richard Greenwich with several different protocols. So they did multiple analysis. So we saw some range of the multiple analysis only from chamber C protocol. At this moment, we are able to send sample many of C, but only single grains from the chamber A sample. So you can see the total different from CM and also CY. So CY and CM is, how do I say? Here. The link between the legal particle CI chondrite. If we take a look at the bulk oxygen aspect analysis. And the right-hand side is bulk elemental abundances determined by INAA. So basically very similar, basically consistent with the range of CI component, but some difference in the titanium, calcium, and magnesium gold. This calcium and manganese is perhaps absence of carbonate. Okay, these two and also several analytical results, several bulk analytical results shows we found some link between the Ryugu particles and the CI chondrite. And as I say, so we did not see any sulfate and or ferrified at this moment. So at this time, so we concluded, we ruled out a link between CA particles and the CY and CM. Okay, this is NanoSim's work, which is my part. This is a STIXM CZN's images. So after we took, at this moment, we did not see any NanoSim's features. But after we acquired the carbon isotopic image with NanoSims, we clearly see the high abundance in terms of carbon 13 from here. So, so number is about 13,000, which is really high. And after NanoSims imaging, so we saw what kind of placeholder grain in here. So based on the TEM observation, this was a graphite. We confirmed this is a graphite. And also this is some carbon concentrated image. So we we confirm this is a nanoglobule. The inside of the nanoglobule contain some amorphous silicate, but amorphous silicate is we are not sure this amorphous silicate is original or some artifact during the TEM or FIB ion irradiations. This is a really interesting features. What we found from the legal sample is this is we found aliphatic rich organics in association with ferrosilicate. So if we take a closer look here, so this is, this is a ferrosilicate a lot, and the ferrosilicate is inside of the ferrosilicate have a lot of organic component. So if we look at the STIXM dataset, so this green area is only showed strong peaks of aliphatic, no aromatic features here. But for example, the nanoglobule on the red part is perhaps nanoglobule. These guys shows aromatic features. So this is very consistent with the previous analysis of the series of nanosims. And so matrix, the blue region is somewhere between this red and green part. So we clearly see aliphatic carbon and also aromatic carbon. So Murchison IOM is like this. So we did not find any aliphatic characteristics from the Murchison. Okay, in summarize, here is a Ryugu particle containing both aromatic and aliphatic rich organics. So STIXM, different from IOM, extracted from chondrite, but similar to carbonaceous materials in IDP and committed build to sample. So aliphatic rich organic is associated with the covalent ferrosilicate. This is a strong link we found is as water lock interactions. But however, the last LPS meeting, so Yapta et al., De Gregorio et al., the result by STIXM is different from ours. So their data set did not show any aliphatic features. However, this data is very consistent with other studies, other instrumentations like microomega or FTIR or TEM-ERS. We are not sure this is some variations in the Ryugu sample, but we don't know yet. But so far we have seven FIB sections. We always see this kind of features. This is very general of features in Ryugu sample. And this is a hydrogen and nitrogen acid composition in organics by nanosynths like this. Aliphatic rich organics, green lesion, and blue lesion is slightly different. So we are thinking this green lesion is precursor both organics, precursor molecules either in the protoplanetary disk or interstellar medium prior to solar system formation. Perhaps Fischer-Tropsch synthesis is one candidate, and then the slightly modified during aqueous alteration in the Ryugu or Ryugu grandparent body. We are not sure yet. And but if we think hydrogen and nitrogen has to be composition, entire bulk means entire images. So gray area is CM. The green is C2, which is Turkish lake or bells. And here is a cometary sample, a comet. And those, okay. So the Ryugu sample is a red circle and a blue circle. These are very similar distributions with the IDPs. So this implies a relatively high delta D and the delta nitrogen values of the Ryugu particle indicate that they are pristine and the potential derived from the at least the outer solar system. And after this is a potential contamination alert. So after we did a neutron activation analysis, the A98 sample shows a thallium strong peak. So this is a projectile. So if we perhaps thallium is not a good indicator if someone used for the cosmic chemical implications, this is be careful. And also we have a series of analysis of carbon particles generated by SCI operation. So this, we have a lot of data set already published in geochemical journals. So when you do organic component measurement, please take a look at these two Ito et al., Takano et al. Papers. And in conclusion, so we did some indications of allocated Ryugu particle with the PH2K. PH2K is my team, and integrated bulk and microanalysis with minimal or non-terrestrial air exposure. The allocated Ryugu samples are similar to CI chondrite based on the analysis of the semi-EDS neutron activation analysis, microprobe, laser fluorination, or isotopic analysis. Everybody knows the samples are enriched in organic component. But here we found aliphatic rich organics in association with phyllosilicate at submicrometer scale, suggesting a link to waterlock and the organic interactions. We found a lot of nanoglobules, aliphatic, perhaps perfect aliphatics, and aromatic rich. Hydrogen, carbon, and oxygen and nitrogen show no mouse composition at this moment. One peroxide graphite found, and which contains extreme 13 carbon rich, and the Si and nitrogen isotopic composition is close to solar. Be careful with the contamination with thallium and also SCI. Okay, so far these 6 research activities. Our paper is a provisional accepted to Nature Astronomy. The 4 red is in preparation. The 4 is in review or editorial handling. So we received 50 milligram so far. The next 50 milligram Ryugu sample is, so we did more collaboration with international team, especially the Open University. We will do a carbon and nitrogen isotopes and the noble gas analysis in bulk. And these 2 are very challenging. We may use ion TOF hybrid SIMS to acquire detailed characterization of organic component, as well as high resolution map by Optrap and TOF analyzer. After that, I would like to do nanoscience work. The Neutron Ct at JPA. This Neutron Ct allow us to visualize hydrogen distribution in Ryugu particle with 20 micrometer spatial resolution. This is very challenging. So these are our new samples, 650. This is a particle. The one thing I have to mention is if you take a closer look at the C209 sample, there is several white particles. This is a real white particle. So right now we are focusing on analysis this white particle. So far this is magnesium, phosphorus, something. So far I only know about that. Okay, so our team is work as a part of JAXA collaboration for science and curatory activity. So the Ryugu data archives from class 2. Class 2 is a potential contamination and not class 1. So all experiments and this activity should be done in a year. So 1 year from we will finish. So this time, strength and international collaboration with the UCLA and the Open University Cosmic Chemistry Research Team. And we would like to make a potential link with the phase circulation at the EU team. So this is just my dream. All right, thank you very much for your patience. So more Hayabusa2 related result comes to this later this year. Thank you.
All right, thank you so much. Audience can feel free to express their gratitude through their digital applause. And for those who have questions, you can digitally raise your hand or you can type a question into the chat box and I will read it to the speaker for you. Give people a moment to get their questions up. Looks like we got a question from Paul Abel. Paul, you can go ahead and unmute yourself.
Polka.
Ohayou gozaimasu. Ogenki desu ka?
Yeah, mamas. This time at 6 a.m. I woke up 4:30.
とても大変ですね。
はい、おかげさまで。
My question is, Moto, when you were looking at the particles from chamber A and chamber C,
Yes.
did you notice anything different? Because chamber A is from first touchdown, right?
Yes.
Chamber C is material from second touchdown after SCI, so maybe particles excavated. Was there anything that you noticed that was different? From your talk, it seems like things are very similar.
Yeah, it's difficult to say because we have very limited number of particles so far, but I can say that the particle from room A and C is a little bit different in terms of CAT scan. The room C is more fragile, room A is more packed. It's kind of hard. If you, how do I say? It's difficult to say. Room C is more fragile, I'm thinking. And also the phyllosilicate. As I showed, some relations with organic aliphatic rich organics and the phyllosilicate, that comes a lot from the chamber C particles. So perhaps that is some indicator of the subsurface sample.
Okay, thank you. Arigatou gozaimasu.
Hi, thank you. This.
Okay, our next question is written in the chat box, and then we'll move to our question that we have from folks over at JSC. So this question is from Richard P. Benzel. Do you have a measurement of H2O abundance?
Oh, this moment, no. But next second round campaign, the sample goes to Open University, and Monica Grady will take a lead to analysis of carbon and nitrogen and noble gas as well as H2O abundances with their eager system. So wait for a second. Thank you.
All right, we'll stay tuned for that. Okay, folks at Aries, you can unmute yourself and identify whoever's asking the question, please.
Hi, I'm Christopher Sneed.
Hi,
how are you?
I'm sleepy, you know.
Okay. I know you had a lot of involvement, or I read your paper about the design of the facility transport containers.
Yeah.
I'm wondering, do you know, are those containers being used for storing the samples as well, or are there different containers for the storage and curation?
We use that FFTC for storage in my glow box.
Okay.
You know, some small container, we use what we called, I forgot, but of course that can be usable, but only in the glow box. But
okay.
Basically we use a FFTC for the storage.
Okay, great. Thank you so much. It's good to see you.
Thank you.
Talk.
Thank you.
Any other talks or any other questions, don't be shy. You can raise your hand or type those into the chat box. We'll give a moment for people to do that.
I'm shy, but yes.
Okay, we have a question from Yoav Kashiv. You can unmute yourself.
Hi, I wonder, how do your results compare with remote measurements of surfaces of asteroids, and especially with regard to the organic matter abundance?
No, we cannot detect. We cannot determine any abundance of the organics at this moment. So this is just adapt from the other researches by Naraoka LPSC or Yabuta LPSC. So we only detect where the organic component or what is the carbon structure, chemical information, and isotopes. So we will see how much organics or carbon component, as I say, the next 6 months. Is that okay with you?
Yeah, that's what it is.
Yeah, but the end of this month, I will I will discuss with Micro Omega team for further collaboration. So how your point, of course, we will discuss with spectroscopic teams.
Okay, thank you.
Thank you.
I think we have time for one more question. If anybody would like to take advantage of that, give a minute. Well, in that case, we can thank Moto one more time. Thank you so much for coming to giving this presentation, especially so early in the morning. I think we owe you some tea or coffee next time we see you.
Oh, yes. Thank you very much for this opportunity. I would like to express my thanks to all of the API and also JSC people. So they are very kind still. Thank you.
Thanks so much, Moto. And for those who are interested in the next seminar that we will have will be in June. So we will see you then. Thank you all so much for coming. And thank you again, Moto, for this excellent presentation.
Thank you very much.